After understanding the basics of the hybridization, now let us move to the types of hybridization. The first type of hybridization is SP hybridization. It is the hybridization in which one S and one P orbitals combine to form two new types of orbitals called hybrid orbitals. Now let us see what happens in this case is when one S and one P, as we know, is spherical, and let us see the P involved is your usually is PZ, because we normally take this axis as Z, this axis as your X, and this axis as your Y. Any axes like this can be taken. Even you can take this axis as your X. See, it is normally we usually have the habit of taking always the horizontal axis as the X axis and vertical as the Y axis. But again, remember, it is actually a relative concept. Now, in case of hybridization and MOT and other thing, we normally take the horizontal axis as the Z axis, vertical axis as the Y axis, and the one which is dividing these two is called Y axis. So let us take this one is your normal PZ axis. So when S and PZ combines, the two types of orbitals formed are like this. One is this, other is this. See, I can draw one separately. This is the one type, orbital, a hybrid orbital form, and the same type, the other one will also be similar to this one. In this case, the two lobes are not of the same size. One is bigger, other is smaller, and they gets arranged in such a way that they have what? A linear shape. Now, why they are arranged in a linear shape? The reason is because this is the only thing, it is the only arrangement in which they will be having minimum repulsions between their bonded pair of electrons. So that's why they arrange it like this, and this is the shape of the sp hybrid orbital. Now, what happens is, this is what happens whenever a central atom undergoes sp hybridization. This is also called a diagonal hybridization. Now let us see the example which can show sp type of hybridization. It can be beryllium chloride, I can show you in this case beryllium. Beryllium has 1s2, 2s2, 2p1. Beryllium even not having 2p1. What happens in this case is it's 2s2, 2p0. So no electron in the p. This is what the beryllium is having, valence configuration. We call it ground state. Now in excited state, what we find is one electron jumps and comes here, so that what happens is these two electron gets unpaired. Now they will be available for what? Bonding. Now this is your S, this is your P. Both of these orbitals combines to form sp hybrid orbitals. This is how we show. This chlorine overlaps one chlorine atom and forms sigma bond. This unpaired electron overlaps, the hybrid orbital overlaps the another chlorine atom and forms a sigma bond. So this is how that we can represent in terms of beryllium, that what happens exactly in the beryllium. Now let us see their structure. It is like this is beryllium. So these are the two orbitals we can have. The one bigger lobe and smaller lobe, bigger lobe and smaller lobe, they get linearly arranged. Now from here what happens is, I can show it to you like this. From here one chlorine overlaps. From here also one chlorine overlaps. So this is what is the exact structure is. It takes angle of 180 degree shape becomes linear, and this is what is BeCl2 beryllium chloride molecule. The next type of hybridization is sp2 hybridization. In this, 1s and 2p orbitals overlap. They mixes each other to form new types of orbitals called hybrid orbitals. So the hybrid orbitals formed are called sp2 hybrid orbitals. So this is what is formed. Now let us see how this happens. When 1s, 1p like this and another p like this. So this is p, and this is s. They overlap. What they form is 3 new types of orbital. Each hybrid orbital will be like this. Now there will be 3 such hybrid orbitals. How they will be arranged in order to have the minimum repulsions of the bonded pair between them? Certainly, as per the valence electron pair repulsion theory, in a trigonal planar manner. So what happens is they get arranged like this with an angle of 120 degree. So they take the shape of trigonal planar with an angle of 120 degree. Now let us see the example which shows sp2 hybridization. The example is, let us take BF3, boron trifluoride. Now in case of boron, we know it's 2s2, 2p1 valence electronic configuration. Now in boron, that means boron in ground state, what we find is these are the 2 pair of electron this is the 1 pair electron which is we are having in the case of s orbitals. This is 1 electron present in the p orbital or the p suborbit. Now boron can have its maximum covalency by what? Making this electron pair getting unpaired. So this electron jumps and comes here. So in boron excited state, what we find is the configuration becomes like this. So this unpairing of the paired electrons takes place in these before the hybridization takes place, so that the covalency is maximum in the case of boron. Now all these 3 orbitals overlap. This is s2p and they form sp hybrid orbitals. All these 3 overlaps or with the p orbitals of the fluorine and form sigma bonds with 3 fluorine in this way, like this. So now let us see the structure exactly. What will be the structure of the BF3 molecule? If suppose this is the boron, this is what is the boron central atom, which is having sp2 hybridized orbitals. From here what we notice in this case is 1 fluorine overlaps here like this, another fluorine overlaps here like this, another fluorine overlaps here from here on this side like this. So these are the 3 fluorines we can have overlapping like this. All these angles becomes what? 120 degree. Shape is trigonal planar. The next type of hybridization is sp3 hybridization. In this, 1s and 3p atomic orbitals overlaps to form sp3 hybrid orbitals. So 4 orbitals are combining, 4 are formed. It will be shown by those molecular species in which the central atom will be having 4 pair of electrons. Now what happens is, so when 1s and 3p's combine, it's almost like this. This is 1s, pz, py, px. So when this pz, px and py overlaps, what happens is 4 hybrid orbitals are formed with the shape like this. So such 4 hybrid orbitals will be formed. How they will be arranged? Definitely, as per the valence electron pair repulsion theory, these all 4 will be arranged in a tetrahedral manner so that the bonded pairs are having minimum repulsions between them. So that will, now what will be the exact structure? The exact structure of the sp3 hybridized orbitals will be like this. It will be like this, with each angle of these hybrid orbitals is of 109.5 degree, and the shape is called tetrahedral. Now let us see the examples of the cases in which the molecular species will be showing sp3 hybridization. Like we can have methane molecule. In the methane molecule, what we find is carbon is having 2s2, 2p2, 4 valence electrons. Now in the carbon in the ground state, what we find is the s orbital is having 2 electrons and the p suborbit is also having 2 electrons. Now in order to have maximum covalency, this paired electron on the carbon becomes what? Unpaired. So in carbon in excited state, what we find is this is how the 4 electron gets unpaired. Now all these 4 orbitals, 1s and 3p, are combined to form sp3 hybridized orbitals. And in this way, all these 4 unpaired electrons overlaps with 4 hydrogen atoms and form 4 sigma bonds. Now let us see what will be the structure of this molecular species. The structure will be almost, this is the main structure of the carbon sp3 hybridized orbitals. Now from here we can see this is how the 1 hydrogen atomic orbital overlaps this sp3 hybridized molecular hybrid orbital. Here there is another hydrogen atom. This is how it is overlapping these hybrid orbitals, and this is how it is overlapping the hybrid orbitals. So these 4 sigma bonds are formed. Angle is 109.5 degree and the shape is called tetrahedral. So this is what is the best example to explain sp3 hybridization. Now let us see some organic molecules which are having sp3, sp2 and sp hybridizations. Let us take first the example of C2H6 ethane molecule. In this we have 2 carbon atoms which will be having 3 hydrogens each. Now each carbon in this is sp3 hybridized. What happens is basic structure is almost like this. This is how each carbon is having 3 hydrogens. Now what we find is, like, let's name these 2 hydrogens as 1 and 2. So in the first hydrogen, what we find is, like, this is what is the situation it has in the excited state, and same is the situation, all these 4 combine to form sp3 hybridized orbitals, and same is the case with carbon 2, which will be having what? 4 unpaired electrons in the sp3 hybrid orbitals. Now one of these orbitals, they overlap, of the 2 carbon atoms overlap with each other to form a sigma bond, and the other 3 of the C2 are overlapping with hydrogens to form normal sigma bond, and other 3 of this C1 also are overlapping with the 3 hydrogen atoms. So this is how these 2 are attached through a normal sigma bond of these hybrid orbitals, and the 3 hydrogens are present with both of these. I can draw this diagram and can show it to you like this. It is almost as like this. This is your C1. With these 4 sp3 hybrid orbitals. This is your C2 is. These are the 4 hybrid orbitals in this case. Now how they overlap is, this C1 and this C2, they together from here are forming a sigma bond. From here, this hydrogen, this hydrogen, this hydrogen, the 3 from here overlaps the C1, and 3 from here overlaps with the hybrid orbitals of the C2 like this. So this is how we have this type of structure is formed, which can be easily represented like this. So how many sigma bonds are there in this? 3 here, 6, and this one. Total 7 sigma bonds are here in this. So this is your typical ethane molecule. Now let us take the example of ethene molecule. In this, there is a double bond between 2 carbon atoms, and this is a simple representation of this ethene molecule. And let's again name these 2 carbons as 1 and 2. Now in carbon number 1, what we find is, this is what is the situation is in the excited state, that all its 4 electrons are unpaired and are present in S in the, it's not sp3, they are present like this, sp2 hybrid orbital. The pz remains, or we can say the px remains as such. One of the p orbitals doesn't participate in the bond, in the hybridization. The reason is because it is believed that it is only the central atoms, that many number of atomic orbitals will overlap or will mix, with which it is actually forming a direct bond. So this carbon, since it was forming a direct bond with the 3 more other atoms, so how many atomic orbitals of this central carbon, carbon number 1, will intermix to form the hybrid orbitals? It will be only 3. So these 3 orbitals overlaps, mixes to form the new type of orbital called hybrid orbital. The 4th one remains as such. The same will be the case with the second carbon, that though it will be having these 4 unpaired electrons in the atomic orbitals, but 3 of these have combined to form sp2 hybrid orbitals. Now, through these sp2 hybridized orbitals, C1 and C2, they all together, both of these also are linked to each other through a normal sigma bond through one of these sp2 hybridized orbitals, and the other 2 are used to form bonds with the sigma bonds with the hydrogen atoms. It's like this. So now what happens to this? These 2 unhybridized px orbitals, they show sideway overlapping to form pi orbitals, a pi bond. How? Let us see this. So this is actually a typical representation. Now let us see this one. The C1 is sp2 hybridized. So it's like this. The C2 is also sp2. So we can show it like this. This is your C1, this is your C2. Both are sp2 hybridized, sp2 hybridized. This is a normal sigma bond. Now what happens is, from here the hydrogens are overlapping these hybridized orbitals like this and forming sigma bond. But what happens is we have unhybridized px orbital 2-way px here with C1 as well as unhybridized 2px with the C2 atom. These two overlap sideways or lateral overlapping, and they form second type of bond, which is called pi bond. So which is represented like this, like this is C, H, H, H and H. So there is another bond, this one, green one. The green one is your pi bond and your black one is your all or sigma bonds. So this molecule has 5 sigma plus 1 pi total number of bonds. Now let us see ethyne molecule. In this, the 2 carbon are having triple bond between them, and there are 1 hydrogen having, both of them, these are having with each other. So let us see how this molecule's formation takes place. In the first carbon, what we know, though all their 4 electrons are unpaired, but since this carbon is combining with 2 more other atoms, only 2 of its atomic orbitals will mix with each other to form sp hybridized orbital. Similar, it will be the case in case of C2 carbon, second carbon atom. Though it's all 4 electrons will be what? Unpaired, only 2 of their atomic orbitals will overlap to form what? sp hybrid orbital. Because they are, each carbon of this molecule is bonded to 2 more other atoms. Now, so one of these sp hybrid orbitals are used to form a sigma bond between them. The C1, C2 uses one of the orbitals like this, and one is used to form a sigma bond with the hydrogen atom. It's like this. Now what happens to these two, your px and py unhybridized orbitals? They both overlap like this to form 2 pi bonds. So what we can say is these two are used to form a 1 pi bond, and this is also used to form another pi bond. Now let us see this in the form of a diagram. This is carbon number 1 and this is its sp hybridized orbitals. This is your carbon number 2. This is how they both actually are attached to each other through this. This is C1, this is C2, and this is how they are attached to each other through the overlapping of the hybrid orbitals, which form a sigma bond between them. And from the other end, they are having what? Overlapping with the hydrogen, which forms a sigma bond. But what we notice in this case is that the px and py orbitals of this C1 and of C2 remains what? Remains as such. They doesn't mix with each other. So their shape remains as such. Both of their lobes are drawn in the similar thing. Now they show lateral overlapping, the px with the px, the py with the py, and they form what? 2 pi bonds. So 2 pi bonds are formed. So which are represented like this, like we write it like this. The green one are your pi bonds. So 2 pi bonds, 1 sigma, 1 sigma, 1 sigma. So there are 3 sigma and 2 pi bonds. So this is what is your ethene molecule is.